Everyone. Welcome to anisotropic minerals. First, we'll do a little review from yesterday's brief look that we did in lab, and I'll show you some basic information about how anisotropic minerals appear under the microscope and how we can interpret what we see there. First, you might want to consider why we use this tool. Under the microscope, we can more precisely identify minerals and classify rocks, and often we can see textural information that reveals the history of a rock in a great deal more detail than what we can see in the field or in hand specimen, so it's just a very powerful tool. You've already seen some of the features of the microscope, and I went over them briefly yesterday. To study non-isotropic minerals, you need to become familiar with some of these additional tools. So the two polarizers, the rotating stage, the condenser lens or lenses, and the Bertrand lens. Today we're mostly going to focus on the function that the polarizers serve, and on Thursday we'll talk about the condenser and the Bertrand lens and how they're used. When using a standard transmitted light microscope, white light of many wavelengths and orientations travels up towards your eye. The light propagates towards your eye, but vibrates in all possible directions. But in a polarizing microscope, a polarizing filter is mounted over the light source, which blocks all but one orientation for vibrating light. Typically, the filter permits light vibrating in the east-west direction to be transmitted as you look down at the field of view. So next, I want to look at what happens step by step in the polarizing microscope. First, the polarizer filters the light. All components of the light vibrating to the north-south direction are blocked, and those components vibrating east-west are permitted through. This means that the intensity of the light is diminished, and that's why polarizing sunglasses and windows reduce light intensity. Next, a second polarizer between the stage and your eye can be added or removed. This one is called the analyzer, and it's north-south, perpendicular to the first filter. The polarizing filters, or nickels in older terminology, are now crossed. That means all light is blocked and the field of view appears black. So why would this be advantageous? Well, if you place a mineral on the microscope stage between the two filters that reorients the light, the initially east-west light can now be oriented differently after passing through the crystal. Some component of that light will now be put through that upper north-south filter and light will reach your eye. Anisotropic minerals reorient the light in this way, and they do it to different degrees. The use of the two polarizing filters is thus diagnostic of the light reorienting property. So we can use it as a tool. Now in lab we did this calcite experiment and identified that not only do anisotropic minerals reorient the light, they actually split it into two rays that refract the light differently because they're traveling at different velocities. The ordinary ray appears to remain stationary, while the split extraordinary ray appears to be doubled and rotates around the ordinary ray when you rotate the crystal. Now, this experiment has a number of important implications for the properties of anisotropic minerals. For one, light splitting is a very important effect. The two rays vibrate perpendicularly to each other and they travel at different speeds. The different speeds mean they are refracted to different degrees, which is why the dot you drew appeared doubled when viewed through the crystal. We can define a value delta, called Birefringence, that is equal to the difference in refractive indices of the two rays. This is simply n slow minus n fast, or the absolute value of the difference between the two refractive indices. So take a moment to think about the following questions. First, would you expect to see small or large birefringence when looking down the c-axis of a trigonal crystal like calcite? In comparison, what would you expect to see when looking perpendicular to the c-axis, like down the a-axis? And then third, what about something in between? You might want to pause for this for a second and jot down some notes thinking about the implications of those questions or what answers you might have to them. All right, so it's easy to see this with calcite because at the maximum possible orientation, the birefringence is extremely large. Other minerals are easiest to see under the microscope because they're not so extreme, and hand specimen crystals just they're not possible to see very easily that way. So here's a diagram showing the light splitting effect for a ray of light passing through a crystal that's first been filtered east-west by the lower polarizer. As with Snell's law before, the frequency is constant. So as velocity drops, the wavelength also changes. So notice the slower light ray has also lagged behind the faster one, and it turns out the amount of lag is the product of two different factors. How much slower it's traveling, so the difference in velocity or refractive index, and also how thick the crystal is that produces the lag effect, because the thicker the crystal, the more it's going to be caused to lag behind. And this slide summarizes these key points for you. So note that now there are two light rays exiting, both towards your eye, where before there was only one. Some component of both of these rays will pass through the analyzer, the upper polarizer that's oriented north-south. Your eye will see a composite wave formed by the interference pattern when they're added together into a single waveform with constructive and destructive wave interference by your brain. So a few notes about light interference phenomena. Depending on the wavelengths of those two rays and how much retardation or lag occurs, they could be in or out of phase when they exit the mineral grain. Some of the light from the interference wave pattern will pass through the upper filter to your eye and be seen as light. Remember that the two light rays are vibrating at 90 degrees, and the mineral is sitting on a rotating stage. So if you rotate the stage, those rays will occasionally line up with the lower and upper polarizers. The one that is perpendicular to the lower polarizer is never permitted through in the first place, so there's no competing ray. And one that is parallel to the lower polarizer is in turn perpendicular to the analyzer. So it's blocked above the crystal from reaching your eye. In other words, as the stage is rotated, every 90 degrees the grain will appear black. This is called extinction. So here's a slide illustrating a bright grain with an interference wave pattern producing false colors. And that grain is the light from it, rather, is blocked as the stage is rotated. So we now have seen three different ways that a mineral grain can appear black under cross-polarized light. One, it can be opaque. So that would be black under plain polarized light, one filter, or cross-polarized light with both filters inserted. So those we don't end up being able to draw many conclusions from. Or it could be a mineral that transmits light, but isotropic, so like the fluorite we worked on in lab. In that case, there's no wave splitting, so there's only one refractive index, there's only one direction the light moves through the crystal, and all light is therefore blocked when the analyzer is inserted, because there's no splitting of the light. Or it can be anisotropic and at extinction because of stage rotation. Later, we will add one more additional reason why this could happen, why a grain could appear dark in cross-polarized light. And all of these reasons can be differentiated and are useful for identifying minerals. Okay, so let's briefly return to the concept of retardation of light. Remember that one of the light rays lags behind the other, and the distance it lags depends on the difference in wave speed of the two rays and the thickness of the crystal over which their speeds are different. So we can do some straightforward algebra by observing that in the time it takes for the slow ray to exit the crystal, the fast ray has already moved beyond that. It has traveled through the crystal and some distance in air. And we know that time is distance over velocity, so we can set the time for the slow ray equal to the time for the fast ray. And the distance of retardation, which here is written as capital delta, is equal to d, the mineral thickness, times a series of velocity ratios. And if we assume that the velocity of light in air is very close to the velocity in a vacuum, which is basically true, this is essentially, it reduces to the two refractive indices, n slow minus n fast, and recall that the refractive index, remember, it's equal to the velocity of light in a vacuum over velocity of light in a crystal. So that's how we got there. So the difference in refractive indices, remember, is the definition of birefringence, and it's characteristic for that mineral in that particular orientation. So the amount of retardation, which is a distance, it's the distance of lag of one ray behind the other, is equal to the thickness of the crystal, or thin section, times the birefringence for that mineral. This, it turns out, is very useful, especially because for thin sections, we know if they're properly made, they are exactly 30 microns thick. Now, what we haven't talked about yet is what colors are actually produced by the interference patterns of the two split light rays that pass through the upper analyzer. First, let's consider a red light source. So every 700 nanometers of retardation, the two light rays destructively interfere with each other and are blocked by the upper polarizer. So that means no light is seen. The same is true for all the other colors in the spectrum, for their own characteristic wavelengths. And also for a mixed white light source, which will add up all the different wavelengths into a combined pattern across the visible spectrum that all interfere simultaneously. The result is this interference pattern of colors at the bottom of the screen, which sort of repeats, but not perfectly. This is a more precise version of that diagram. This is an interference color chart, increasing from black on the left, which means there are no split rays, there's no birefringence, there's no retardation, across to very, very high retardation and interference on the right. The repeating cycles are all about 500 nanometers apart, which are called orders. So first order, second order, etc. First order colors range from black to that first pink color. The second order colors continue up to the second band of pink, and etc. In general, interference color patterns become less saturated as they increase to the right. So to use this productively, you need to get familiar with these colors, which can help you identify the birefringence of the substance you're looking at under the microscope, and we'll practice with that in lab over the course of the next few weeks. So here's a version of this chart that has more labels. So this type of chart is available in the back of most optical mineralogy texts. So if you have your own copy, there should be a version of this chart that folds out probably from the back cover, and we will use it a lot. The chart shows retardation of light in nanometers on the x-axis, slide thickness on the y-axis, and birefringence as a series of diagonal lines that intersect the top and right surfaces. So remember that we found that retardation equals thickness times birefringence. So all three of these variables are related. And let's say that you have a thin section of standard 30 micron thickness for a rock containing the mineral olivine. If that mineral is pure magnesium olivine, it is forsterite. So that has a birefringence of 0.033, and it's marked with a blue arrow on the top of the diagram. So trace that diagonal blue line back to the arrow, along the arrow back to the 30 micron line, and you will see the retardation of 1,000 nanometers that is predicted, which corresponds to an interference color of second order orange. And then what about phaolite, pure iron olivine? So that has a higher birefringence with a value of 0.052, which is marked on the right side of the diagram. Again, follow the diagonal back to the 30 micron line, and you can see the retardation is about 1,575 nanometers, and the expected color is third order orange. So olivine can have any composition between those extremes. An intermediate composition mineral might therefore have anything between second and third order orange colors. So spend a few minutes looking at the other examples. Quartz has much lower birefringence, and it only has interference colors of first order white. So this is actually how thin sections are normally tested for thickness. The rock contains quartz. The person preparing the section will check the interference colors of the quartz and will continue to grind the slide down until it is all has an interference color of white. Anything higher, so into the cream or yellow colors, and they'd know the slide was too thick and they should keep grinding it thinner. This is harder to do in a rock without quartz, and other index minerals have to be used instead. You should also consider calcite. Calcite has such high birefringence that it's completely off this chart. It's way off to the right in these very, very high pastel colors. And there's one more issue to consider, which is actually how the mineral grain is oriented on the microscope stage. Remember that these minerals are anisotropic, which means light behaves differently when it travels through the crystal in different directions. So what effect does crystal orientation have on birefringence and interference color? All right, now we go on to this slide. So to address that question, we have to step back a little to do some additional definitions. Remember that isotropic minerals have the same light properties in all directions, and anisotropic minerals do not. They split the light into two polarized components, and the light travels at different speeds in those components and also in different directions. It turns out there are two types of anisotropic minerals. One type has two refractive indices, the other has three. These types still only split the light into two rays at a time, but the speed of light in those two rays varies with direction through the crystal. In the first kind, there are two possibilities, and in the second kind, there are three. So the speed of light in those two rays varies with direction. This is the most important detail that I want you to notice here. And because of their geometrical properties, there are also either one or two special directions where it turns out the light isn't split at all, where only one refractive index can be observed, and it mimics an isotropic mineral, but only in that orientation. These are called optic axes. So the two categories of anisotropic minerals are uniaxial and biaxial. This week we're working on uniaxial minerals. They have two possible refractive indices and one special direction where light won't be split at all, the optic axis, hence uniaxial. Biaxial minerals have three possible refractive indices, and they actually have two optic axes, hence biaxial. And this week we're only doing the uniaxial. Next week we'll get into biaxial minerals. So Snell's law applies here just like it did in isotropic materials. But depending on crystal orientation, the speed of light, or in many cases the speed of each ray of light that's been split, is different. There's also a crystallographic control on the number of refractive indices that a mineral has. Isometric minerals, unsurprisingly, I hope, are isotropic. Uniaxial minerals have symmetry about the C-axis. So tetragonal minerals, trigonal minerals, hexagonal minerals, those minerals that tend to form elongate prisms like quartz or calcite, these fall into that category. All the other examples have less symmetry, considerably less symmetry, so they are all biaxial. This is just a summary slide for your notes, and to make sure we're all on the same page. If necessary, pause it here, jot down any notes you might have or any questions that have come up. And note that even in biaxial minerals, which have three possible refractive indices, the light can only be split into two rays at a time. The speeds of those rays depend on the crystal orientation in a more complex way than uniaxial and isotropic minerals, and we'll get to those next week. Okay, so to relate this more clearly to crystal orientation, consider a hexagonal mineral like the one shown, which you could imagine is a quartz crystal. Note where the highest order of symmetry is, like the highest order of rotational symmetry. That should be the C-axis, right? So as you look down the prism, that's where the C-axis is located. And it has six-fold rotation or three-fold rotation or something like that. That C-axis, or for a tetragonal mineral, would have fourfold. So the C-axis is vertical in this case. And A and B, or A1 and A2 if you like, are the same length crystallographically, and they're oriented perpendicular to C. So if you could look down the C-axis, all the light traveling up at you through the crystal would propagate along the C-axis, and the wave vibration directions would be in the A and B directions. And A and B have the same crystallographic and atomic properties because of crystal symmetry. So would you expect the light coming up the C-axis to be split into two rays that behave differently? And what about a ray traveling along the A-axis, or on this diagram it's labeled A1, perpendicular to C? Some of it can vibrate along the A2 or B-axis, and some is going to vibrate along the C-axis as it is propagating towards you on the A-axis. So based on your thinking, where would you place an optic axis? And take a moment and maybe jot down a note about what you think is likely here. So, if you said the C-axis is the optic axis, you were correct. Light travels up the C-axis, like the vertical line in this top diagram, and it vibrates in the same manner in the B or A directions, because A and B are identical and symmetrical. So that light ray won't be split, and there's no induction of an interference pattern. So if you put the analyzer in and you have a crystal on your stage oriented in this direction with light propagating along the C-axis towards you, it will appear black, even if you rotate the stage. So it will mimic an isotropic mineral. But in any other orientation, you will see something different. You will see light splitting. So light traveling along the A-axis will be split. One ray will vibrate in, say, the AB plane, and the other in the AC plane. at right angles. Those are not symmetrical because the B and C crystallographic axes are different lengths, they have different atomic makeup, different electrical patterns that slow down light differently. So this is the orientation with the most different possible wave speeds between the split rays in the crystal. So you would see the highest possible birefringence because the refractive indices of those two rays are as different as possible. Therefore, that orientation would show you the highest possible interference colors on that chart because it produce the most light retardation. If, on the other hand, you look through the crystal at a more oblique angle, like the diagonal ray shown on the top diagram, you should see something in between. You'll see some component that's the same as what vibrates coming up the C-axis, and some component that's intermediate, not quite as extreme as perpendicular to the C-axis, but intermediate. So this is a really important observation. It means that depending on how a crystal is oriented on your stage, you could see anything from no birefringence and a black interference color down the optic axis, all the way up to the maximum possible birefringence and highest order interference color for that mineral, but you could see anything in between. So when looking at a microscope slide with many crystals of the same mineral, you'll see many different interference colors as you rotate the stage. And because they're oriented differently, they'll also all go at different times, turn black at different times with stage rotation. So you need to hunt for one that has the highest order interference colors to try to identify maximum birefringence. And that maximum birefringence is what is characteristic of the mineral and can help you identify it. So we've actually skipped over something. I didn't have you think about this very hard, but you might have thought about it in the back of your mind, and that is it the ordinary ray or the extraordinary ray in a uniaxial mineral that is faster? It turns out it can be either way, but it is specifically characteristic of each given mineral. So in calcite, the extraordinary ray has the lower refractive index, it's the fast ray, while in quartz, the ordinary ray is the fast ray and has the lower refractive index. So this is actually useful identification information. In some minerals, the fast ray is the ordinary ray, and in others, it's the extraordinary ray. Just by convention, we name those where the extraordinary ray has the higher N value positive, so quartz is positive. And those with the opposite relationship are called negative, like calcite. So now you should be thinking, how can we tell those apart? I said that it's useful, so we should be able to tell it apart. Birefringence is just the difference between the two wave speeds. It's an absolute value. Interference color doesn't tell you which ray is fast, it just tells you the difference between the two. At least not by itself. But the designers of our microscopes were very, very clever. The microscope is equipped with an additional plate called the accessory plate. In many of the microscopes we were using in lab, these had been taken out and set aside, but they are available, and there's a hole over the stage where it can be inserted. The plate is not normally inserted all the way, but it can be pushed into the field of view over the microscope stage when you want it there. And it contains a mounted mineral grain of known thickness and orientation, so it produces a known amount of retardation and in a known direction. Typically, this is either a crystal of quartz or a crystal of gypsum, and it is made so that it will show exactly one order of interference color, so 540 nanometer retardation, so that when you insert it, it turns the field of view bright pink, first order pink. More importantly, we know exactly what way it's oriented, so we know which direction is the fast ray in the plate and which direction is the slow ray, and it doesn't rotate when you turn the stage, it just stays in place. And the plates are labeled, and were deliberately mounted in the correct position. So this won't do any good if the mineral or the plate were oriented so that they were at extinction. So to make it useful, the plate is oriented 45 degrees from extinction to show as much of the interference color as possible. And if you want to compare it to an unknown mineral on your microscope stage, you orient that one the same way. So first you'd want to line it up at extinction and then move it 45 degrees away from extinction and then insert the plate. So consider the example on the top of this slide. At the very far end, on the left, the light exits the lower polarizer and is vibrating up and down. The mineral sample is oriented 45 degrees from extinction, so the split light rays it produces, due to anisotropy, are not blocked by the analyzer, not fully. So it's as far away from extinction as possible. So now note that the slow ray, which is the one that's vibrating in the upper left quadrant, it's labeled on there, and the fast ray in the upper right quadrant have been split, and that causes some lag. So the slow ray is going to have a retardation behind the fast ray. And when the plate is inserted with its known orientation, in this case, it has its slow ray also rotated to be in the upper left quadrant. Now, the plate is a permanent mount. It can only be inserted one way, so it's always going to have the slow ray in the upper left. So, slow ray in the upper left on the mineral, slow ray on the upper left on our accessory plate. That means that the same light ray that had already lagged behind now is forced to lag behind even more, and the retardation of the two rays increases, and a higher order interference color is observed. Now, for comparison, the second ball, below the first one, has the opposite sense of retardation in the mineral grain that's unknown on your microscope stage. So you say it's rotated 45 or 90 degrees away from the previous example. The accessory plate on the far right is still oriented the same because it can't move, but the unknown sample is vibrating in the opposite sense. Its fast ray is now in the upper left and the slow is in the upper right. So the split light ray will lag behind so that the upper right ray lags, but in the accessory plate the opposite happens and it's able to catch up essentially to the ray that had previously been the fast ray. The retardation between the two rays has now been reduced. It could even be reversed. The one that had previously been slow could now catch up and pass the fast one, so it could become the fast ray. And the lower order interference colors are then observed. So this only works because we know the rotation of the accessory plate, but that makes it very powerful for identifying fast and slow rays in a crystal of interest on our microscope stage. So how do we actually do this? It is most useful. It can be used on any mineral grain, but it's especially useful for minerals that grow in an elongate crystal habit. And for uniaxial minerals, this is often the direction of crystal growth along the c-axis. So if you identify that that's the case, that that's the c-axis, you can figure out if the c-axis, the optic axis, which has the ordinary ray propagating along it, if that is the fast ray or the slow ray. So the mineral has been rotated, so it is 45 degrees away from extinction, and it's oriented parallel to the edge of the plate, so southwest-northeast. And then the plate has a known slow-fast orientation marked with that little arrow. The long arrow indicates high refractive index, so that's the slow direction. So remember, long arrow, slow, light ray. And it turns out our crystal on the left is oriented the same way. The slow ray is the c-axis. It's the elongate direction of the crystal. And so in that case, you'd see addition of retardation. You'd see a higher order interference color, 540 nanometers higher. It should be exactly one order up. And it is called length slow. And that's characteristic of the mineral, and it tells you something about optic sign. In the opposite case on the right has experiences subtraction. So you would see reduction in interference color, and that would be called length fast. So this handout is one I gave you in class. It has the whole interference color chart, and on the left side the chart has been extended into negative values to show a mirror image. Remember that birefringence is an absolute value, so so-called negative interference colors are just duplicating the positive ones. It just means that maybe what was previously the slow ray, when you add the accessory plate, has caught up and become the fast ray, has passed what had previously been the fast ray. So consider the crystals shown. There are lots of examples here. They're all from grain mounts. So the minerals are not of uniform thickness. They have higher order interference colors in the center of the crystals than at the edges because of the difference in thickness. So it helps to pick a very distinctive interference color, or maybe the edge, so that you can watch how it changes as the plate is inserted and removed. In the top right example, the color in the middle of the grain increases when the plate is added from first order yellow to second order orange, indicating that it is length slow because the colors increased, so the retardation added. The bottom left example, on the other hand, shows first order gray being reduced to first order yellow. Now, you might look like you could be fooled and think it increased, but remember, it has to increase or decrease by exactly 540 nanometers of retardation. So it could only actually be subtraction because it would be too small a change to be addition with the wave plate, with the accessory plate. You might want to pause here and look at the handout and look at the other examples. I also, on the next slide, have a couple more examples without pictures of crystals, but just of color changes on the chart. So here's another set of examples mapped onto a chart showing addition versus subtraction for an initial starting interference color. And I encourage you to pause here, look at these examples, look at the handout I gave you, and make sure you understand what's happening. Or that if you don't, write out some questions that you can bring to class on Thursday. All right. There are a few additional properties of anisotropic minerals that can be observed under the microscope, now that you know a little more about how they work. So in plain polarized light, which means just the analyzer removed and only one filter in place, it's possible to see natural mineral color. So not all minerals are clear, some are tinted. But you can also sometimes see a special property called pleochroism in anisotropic minerals. Pleochroic minerals produce an intensity of color or tint when in different orientations. This means that when their colors appear different as the stage is rotated and the crystal is lying in a different orientation, it's only because of the lower polarizing filter blocking one of the rays partially or fully that are split. So the two rays are still split, but you just don't have that upper polarizer in to see the interference color pattern. But you can still see this effect moving one of the rays on occasion, or seeing less of it. So the two split rays have different absorptions, it turns out, in the visible spectrum in these minerals. So minerals like hornblende and biotite are very strongly pleochroic. Some are more weakly pleochroic. But either way, it's a useful property to observe for identification purposes because not all minerals exhibit this effect. And in this case, you can see the amphiboles, the hornblende crystals, which are labeled HBl, change color as they are rotated 90 degrees from the picture on the left to the picture on the right, while the plagioclase crystals are white and they stay white, they don't change. And you can actually, if you pause here and look closely, you might be able to see the amphibole cleavage in the hornblende crystals. There are a lot of cracks, some of them are aligned, and some of them make nice little diamonds. And actually, it can be useful to identify pleochroism as another way to identify the extraordinary and ordinary rays and their properties in a mineral. So first, we want to find a mineral grain with very low interference colors, ideally black. So you are looking down the optic axis or as close to it as possible. This is with the analyzer in. That means you are only seeing the ordinary ray propagating along the C-axis. If you remove the analyzer, you can then note the color. So now you know the color of light in that crystal for just the ordinary ray. Put the analyzer back in, look around for another mineral grain with maximum interference colors, so it's lying with the C-axis horizontal. And then you want to rotate it till it's extinct and remove the analyzer and note the color. Rotate it 90 degrees and note the other color. The one that is different from the ordinary ray indicates both the orientation of the extraordinary ray and the color of the extraordinary ray. So now you know both which is which in that crystal, which could be maybe along, you can basically do this to identify elongate axes, whether it's the C-axis or not, along the axis. And in fact, you could go back and do that fast or slow ray method with the accessory plate and determine if the mineral is uniaxial positive or negative. And in the back of optics texts, there are charts that list uniaxial positive and negative minerals, and with these other properties like maximum birefringence, the amount of relief you see in plain polarized light, any cleavage you observe, and color or tint, you can probably definitively identify the mineral now. So just a final example. Tourmaline is a great example of a uniaxial mineral with strong pleochroism, particularly dark tourmaline. The dark round grain on the left is oriented with the C-axis vertical. So on the right, when it's been rotated 90 degrees, it's still dark. And this is in plain polarized light. You can confirm in cross-polarized light that it is black, so the c-axis is vertical. Whereas the more elongate grain in the lower right portion of the left-hand image is cut parallel to C. So c-axis is lying flat on the microscope stage. This one should show maximum birefringence if you inserted the analyzer. And in plain polarized light, it's highly pleochroic. You can see that the color changes dramatically. So you could orient this one so that it is at extinction with the analyzer in, and then test the two colors, which looks like it's been done here. The orientation on the left shows a color similar to the vertically oriented grain, so that should be showing the ordinary ray. And the extraordinary ray orientation on the right receives no light from the lower polarizing filter, so all you're seeing is the other ray. So on Thursday, in class, I want to quickly review anything from these slides that was confusing or unclear. So please bring your questions with you to discuss. You can also back up and look at these slides again, watch this lecture again. It's only about 35-40 minutes, so you should have time to do that. I'll also show you a special type of model or diagram for keeping track of the refractive indices in uniaxial positive and negative minerals. And then I'll explain the purpose of the conical lens and the Bertrand lens, which turns out to be another way to look for whether a mineral is uniaxial and uniaxial positive or negative. And we'll then be ready for lab on Monday, where you'll get to try that out yourself. So I hope you're enjoying the snow, and please stay safe, and I will see you on Thursday. Bye.